generally our goal here is to talk about AI methods that are often traditionally used for prescriptive modes of what software agents should do in a certain situation that we've been applying in a descriptive way to apply to these rational models to describing how people behave. And I'll talk a little bit about both in terms of simulating how a person might behave in responding to, for example, a building environment, and also how using it in a descriptive way inside an agent or an autonomous system, now we can understand how an AI algorithm can generate very good autonomous behavior that doesn't compromise the human agent system interaction. So that's what the explainable AI part, where we talk about some of the issues that when you have an autonomous system, even if it's doing the right thing, if the people don't understand why it's doing the right thing, they're still not going to like it. But I'll first talk about the basic agent architecture we use to underlie both of those research directions. And really, so from our applications at ICT, we usually look at understanding human behavior in a social scenario. So we haven't specifically worked at modeling people in a building scenario, but hopefully you can see how the methods here can apply to those sort of situations just as easily. So a lot of times we worked on a specific scenario of the city of Seattle looking into a terrorist attack and trying to understand how people would respond in that situation. Looking at designing security systems and trying to understand, again, how hypothetical candidate security systems would be reacted to by people. Understanding how people respond to radical ideologies being spread over social media, etc. And across all these different scenarios that we look at, there's commonality, common threads of we have different people here coming in with their own subjective perceptions, their own beliefs, their own goals, their own conflicting desires, as well as their own beliefs about other people, their own beliefs about the social system they operate in. And every policy you try to implement is going to have some immediate effect. Your target goal of you want to get people to stop spreading dangerous messages, but then people are going to react to that, and they're going to find ways to circumvent your policy, and then people might find ways to counter the people who are circumventing the policy, and there's second and third order effects that percolate down the road. And when people try to anticipate these second and third order effects, you often get a lot of sort of tunnel vision. You get sort of you form a hypothesis, and then you sort of confirm your own hypothesis, even as much brainstorming and groupthink comes into play as well. And so one of the things we try to do is augment the domain experts' knowledge about and trying to anticipate responses with sort of automated systems that can explore perturbations and explore more possibilities than is possible in a human setting, but maybe perhaps guided by that general human knowledge. So that's sort of the general problem we look at, is how to use AI technology to sort of augment human knowledge, sort of expand the depth of exploration as well as the breadth of exploration through simulation. And so, so basically our system that we've worked on is called PsychSim. I'll talk a little bit about the technical details, but not enough not enough time to talk about it in detail, but I'm happy to talk about it offline or in questions. But if you think about modeling a city, you can have each agent represent an entity in the scenario, perhaps down to the individual level, or you can try to aggregate each agent represents a different neighborhood. And then you're going to execute the simulation to answer questions. Hopefully these agents are sufficiently accurate proxies for the people, so that if you try out a policy in simulation, you get an accurate enough response to influence your decision making. But in particular, when we say agent-based modeling, that means a wide range of things in the world. Sort of the earliest agent-based models they had very simple rules that they followed. If multiple of my neighbors change color, if a majority of my neighbors change color, I will change color. All the way to and of course agents got more and more complex since then. And in particular, when we look at what we need out of our agents, we've identified several features that are common in AI, but less common in social simulations. So in particular, we see a lot of social scenarios have uncertainty. So for example, in the terrorist attack scenario, people are not sure whether they're going to get exposed to anthrax. They're not sure about how dangerous it is. If they leave, they're worried about their job. If they leave town, try to evacuate. And so from an AI point of view, that means we want probability. We need to be able to represent the uncertainty that people have, their uncertain beliefs, or if you want to have if you want to be able to capture the fact that, especially in social situations, right, people can't read minds, so there's always uncertainty about when we think about other people. We're never 100% sure about what other people are going to do. And so it's really almost impossible to represent social reasoning with any fidelity if you don't capture uncertainty. Similarly, people have conflicting goals. If I don't want to get anthrax, I could just stay inside, but I also need to make money, so I need to go to work. Generally, if you have a situation where there are no conflicting goals, it's probably very easy to predict what people are going to do. most of the complexity of trying to predict what people are going to do is understanding how they're going to make trade-offs between those conflicting goals that they have, and how different people are going to make different trade-offs among those goals. And then, of course, people have theory of mind. We're not talking about a single person sitting at home just operating in isolation. They're often operating in a social context. And even if they're not operating in a social context, it could be just one person interacting with an autonomous system. People are going to form a theory of mind about how that autonomous system works. And so even just with that dyadic interaction between a person and an autonomous system, there's still a theory of mind at play. And the system needs to understand that person's theory of mind if they want to make reasonable expectations of that person's behavior. And to do that, this is something that's common in AI, is to use recursive models where the AI system is going to use its own reasoning as a model for the person's reasoning. And of course, maybe some mismatches there, but you might need to capture what the person thinks differently from what the system does. But as a computational construct, it's a very well-studied mechanism to be able to predict how people are going to behave by reusing your own computational machinery. Okay. So I'm going to go very quickly through what the AI model we're going to use. Basically, it's a Markov decision process, so there's some probabilistic effects of actions. And the actions in this case could be, I'll try to give you a brief graphical representation. You could leave Seattle, evacuate. This is a disaster response where we have some rectangular nodes representing the actions. And this is a representation we use basically to present the sort of an abstraction over the underlying quantitative AI models. We present it to people for both experts to help in modeling the people, as well as to explain to the users how the system might actually be working. But this is going to be a model of a person. So this is a model the system is going to try to create of a person that it has data about. So they have particular options that the person can make. These are the actions they can take. They could leave. They could take an antibiotic. And then there's some sort of state features which represent variables characterizing the situation, both before the action on the left and the effects of the action on the right. So they have a job, and that job might get, if they have a job before, they're more likely to have a job afterwards, so it's a green dependency. If they have a high level of risk before, they're more likely to have a high level of risk afterwards. But you can also have, your actions are going to moderate those effects. So, for example, if you leave, that's going to have a negative effect on your job. You're more likely to lose your job if you leave, but it's also going to have a negative effect on your risk. If you leave Seattle, you'll be less at risk. And so these dependencies are sort of a graphical representation of a probabilistic effect table that's inside the agent, representing how the person is going to anticipate these effects. So these are going to be a model of what effects the person anticipates for its different actions. And this is what the agent can use to try to predict what the person's how it's going to act. And the final thing, there's some observations as well, but the key note here at the end is also the reward function, which is going to represent the person's goals. So this represents basically how important are certain features to the person. So financial stability is important, and personal survival is important. So they don't want to die, and they want to make sure that their basic needs are met through buying stuff. And so there are two positive links green links from financial stability to the reward, and from personal survival to the reward. And different people are going to have different numbers on these links, but this is kind of the basic dependency structure we're going to talk about. And what we can do now is, of course, this is the challenge, right? If the big challenge, when we first started doing this work, we first thought, oh, it's going to be really hard to represent people's decision-making we need to modify our language to be able to capture people. And it turned out that actually wasn't the hard part. The hard part was, well, no, we have a very powerful language. We can represent a lot of different people. The problem is if we want to model a specific person, which model within this whole space of parameters is the right model to choose? What's the right link structure to use to capture a specific person that we have data on? And so this is actually, what we ended up doing was we took some data, we actually had data from a study conducted in Seattle, and what we did was, well, the first thing we did was we took the analysis that the social scientists had done, and we tried to figure out, well, what model sort of captures the highest correlation dependencies or whatever statistically significant dependencies existed in the data. And we're going to build a model based on those. We captured links based on a statistical analysis. And then we compared that model against, okay, well, if this is what everybody in the study, if this is how they're viewing the problem, how would that match against what people actually responded to in the experiment? So we plug this agent in, and we take all the different beliefs and goals that the people put in the survey, we plug those into the agent, and see what decision it makes. And does it decide to leave or not? And it turned out that this model that was taken from the statistical analysis, it actually captured 143 people out of 627, which is not bad, but you couldn't publish a paper about this, right? You build a single model and it captures only 143, basically less than a quarter. that's not going to get you anywhere. And so what we try to do is like, well, are there ways in which we can change the model automatically using the data to capture more people? So what we did was we basically created a model that kind of just searched through, okay, what if I remove this link? What if I add this link? What if I make this link stronger? Basically perturbations on the original model. And then we evaluated the perturbations on the data to see which ones match more people or less people. Try to perturbate, doing this in an automatic way, searching through possible hypotheses that were specified ahead of time, comparing against the data. And importantly, we don't want to just figure out what the best single model is. We're not required to come up with just one model, right? This is a multi-agent simulation. We can have multiple agent models in here. So we're gonna basically, we have 600 people. The question is going to be, maybe there's a single model out there that captures everybody. That would be great. But maybe we need 600 models to capture 600 people. That would be not so great. But it might be, maybe that's required. And so we started with the base model, and we actually, after the system was running for a while, it came up with this alternate version of the model where what you can see some of the differences are, some of the things that are X'd out is, so there was an expectation in the initial model that was created by the initial analysis that if you leave, your risk is going to go down. But it turned out a better model that fit more people was that if you didn't think that leaving would actually decrease your risk. And if you didn't think the antibiotic would actually work, so you remove the link from the antibiotic to the risk, that actually turned out to be better to capture more people in the Seattle world. And he thought that leaving would decrease your financial stability. That would also capture. It ended up capturing 192 people, which is 50 more people. Still not great though, right? That's still only 30% of the population. So, but then again, we don't have to stop. We can keep going, and we say, okay, well, it turned out the statistical analysis model was the next best model. It captured 123 more people, and we can keep capturing more and more models here. Different perturbations, capture more people. And in the end, it turned out that with 5 different models, we could capture 80% of the participants, 10 of them cover 94% of the people. And now we have some choices here, right? We can make this, we can sort of bias ourselves toward having more aggregated models. We can say like, all right, well, five models is pretty good, it's 80% accurate, but it's still reasonable. Or we can try to really get fine grain and get to 17 models to get 97% accuracy. And each model is a simulation object, so we can run it, execute it as a simulation. And it's also in this graphical form, so we can do comparisons. We can actually identify what are the differences between this group, one group that's leaving, and this other group that's not leaving. We can actually just do it like a diff between the two graphs and say, oh, well, this group has a negative expectation here, and this one has a positive expectation here. So try to put this into a sort of transparent language where we can sort of do inspection on it, to compare different models, allows us to sort of both get a sort of a structured model for searching and identifying accurate models, as well as explaining after the fact why the different people are behaving differently, in addition to just generating predictions. We've built a lot of applications using PsychSim. I'm not going to go into a lot of time about that. Also model around social behaviors built on top of the same language. But I probably run out of time. I want to talk a little about, I was talking about explainability, and one of the challenges is that we want to make sure that the agent, whatever the agent is doing, if you think of this, we use the same infrastructure for building autonomous systems, we want them to be transparent to people for a lot of different reasons. One is validation. If we learn the model from data, we want to know why how the data became translated into this abstract model. We also want to be able to understand the model. Like if you look at two groups that are behaving differently, why are they behaving differently? If you run them in simulation, if you run simulations on Seattle, we want to understand, okay, we don't want to just look at, evacuations dropped 30%. That's an answer, but it's not a great answer. We also want to understand what was it in the intervention we might have tried out that led to that. Why did people change their behavior under one policy versus another? And also, importantly, when people are interacting with an autonomous system, we also are concerned about trust calibration. If the agent is making recommendations, for example, or providing some sort of, if it's doing anything to sort of restrict people's behavior, then are people going to try to circumvent it, or are they going to trust the system that it has its best interest at heart? And quantitative models like POMDPs have probability tables, utility functions. They're typically opaque, because there are a lot of individual numerical dependencies that are getting chained over projections into the future, and so it becomes really hard for a person to understand why the end decision by the agent is what it was. But on the other hand, the graph structure that we can use, it does have variables that have meaning to people, right? We have things like risk and finances and jobs, and so those are things. If you have that factored representation, where we have the different variables, there is some hope that they're potentially translatable to humans. Which is unlike neural networks, because so one of the issues we do is that we do a little bit of machine learning, but we try to constrain the learning to be on a representation that is potentially transparent. So one of the problems with neural networks is that, yes, you can probably learn a more accurate model than our model can, but at the same time, you're not going to, the individual nodes are not going to have meaning that can be communicated. And so one of the challenges for explainable AI is explaining neural networks. We try to avoid that problem by starting with a model that is already a little bit more explainable than the typical machine learning model. But we sacrifice some accuracy by doing that. We restrict the representation ahead of time. I'm going to skip this slide. But one of the things we found is that we can actually take we generate some algorithms for, this is Ning Wang's work, on automatically generating explanations. So basically adding text that would convey certain components of the POMDP, not the whole thing, because the whole tree of reasoning is way too complicated, but identifying which specific aspects of that reasoning, if exposed, would be helpful in getting people to understand how the system works. And we're talking about calibrating trust here, so explanations that didn't necessarily increase the trust, but actually to sort of get people to know, or it didn't necessarily increase compliance. What we actually found was that the people who knew when not to trust the agent, so when the agent is wrong, the people kind of knew that they should ignore the robot's recommendation, for example, this is a simulated robot, and not trust, they actually trusted the system more than the people who just complied with the robot every single time. Because the people who complied with it ended up being wrong, and they didn't really know why. The people who knew when the robot was wrong and were able to actually behave they were able to correctly override the system's recommendation, actually showed more trust and were actually happier with the system. Now, of course, there are lots of individual differences here, and we can talk a little more about how you can detect some of those individual differences from behavior. But it actually, once you can do that, it actually fits naturally into the POMDP belief update, recursive models again. We can actually have the agent use a theory of mind to understand what type of individual they're dealing with, and actually basically fine-tune their decision-making to account for the individual differences in the people they're dealing with. And so I'm out of time there, so I'll stop, but I'm happy to have time for any questions.